So for section 6.4, we're going to be looking at finding the length of a plane curve. So the issue is going to become finding the distance between 2 points of this straight line. We know we have our distance formula, but the problem is how we can actually calculate the length between 2 points that is no longer linear. It is a curve. So again, we have a smooth curve over a closed interval from A to B. So what basically happens is we're going to take a section of the curve, and as I just mentioned, we know the distance between 2 points is a straight line. So because we have a curve, what we're going to do is start taking this curve and dividing it into smaller and smaller line segments, and then adding the distance of all those line segments together. So again, the line segments tend to become better and better approximations to a curve as the number of line segments increases, or as the length of these line segments becomes smaller and smaller. So again, we can use Riemann sums to approach the definite integral. So like I said, shorter line segments will provide a better approximation to the curve. There is a formal proof in your book as to where this formula that we're about to talk about comes from. It's on page 439 of your book, and it is an application of your mean value theorem. So if you have a function y equals f of x and there's a smooth curve on your closed interval a to b, then the way we can calculate your arc length is defined by your antiderivative, again a to b, of the square root of 1 plus f prime of x to the second power dx. So there's 3 different ways you can look at this particular formula. One is like I just showed you. So you have to integrate from your closed interval a to b, the square root of 1 plus the derivative of f of x, and then squaring your derivative. Or remember, another notation for f prime is your dy dx. So that is, again, if it's with respect to x in the form of y equals f of x. If your function with respect to y, where x is equal to g of y, then again, remember your bounds will be in terms of y. These will be y values. And again, it's going to be still the square root of g prime of y to the second power. You have to take the derivative of g of y. Again, dx dy would be your other notation for g prime of y. There's also another arc length formula we'll get to in chapter 10, which was for parametrics and polar curves. But we'll get to that in chapter 10 later on. So there will be another arc length formula when we get to chapter 10. So these could be calculator or non-calculator questions, but again, since the straight line is the shortest distance between 2 points, our arc length is always going to be an underestimate for any graph that is not a straight line. So find the exact arc length of the curve over this particular interval. So for example, if you want to do this on the calculator, now one thing I need to warn you about, your calculator has to do a lot of math with the arc length formula. You need to be patient. It may take a minute or two for the calculation to be done. Again, so here's my f of x. So f of x they're giving you as 1/6 x to the third plus 1 over 2x. So what I need to do is to find my arc length. I'm simply going to take the antiderivative. Again, they're giving my bounds. Lower bound of 1/2 to 2. It's going to be the square root of 1 plus my f prime of x to the second power dx. So we can let our calculator do a lot of this work for us. So again, I'm going to go to my y equals screen, and I'm going to type in my f of x, which is going to be my x to the third divided by 6 plus 1 divided by, make sure you put parentheses around that, 2x if you're not using your fraction bar. So now you can go under your calculator under y2, and you can have the calculator find the derivative of what's under y1. So go to your alpha window, choose option 3. And again, I want to take the derivative of what's loaded under y1, and x equals x. So now when I go on my home screen to find my arc length, I'm going to go under alpha, window, choose my integral from 1/2, which I'll just type in as 0.5, to 2, type in the square root of 1 plus, remember I have the derivative loaded under y2, squared. So I end up with about 2.063. That's how we can do arc length problems on the calculator. These also may be no calculator questions. So here's an example where I want to find the exact R length from x equals 1 plus y to the 3/2 from 0 to 4. So now we know the arc length formula is going to be, again, from C to D, square root of 1 plus g prime of y squared dy. You want to clean up this integral and put this most simplified form of into your integral. So again, I know that my g of y is equal to the function 1 plus y to the 3/2. So then when I find g prime of y, when I go to find the derivative, I know the derivative of 1 is 0. The derivative of y to the 3/2, again using your power rules, 3/2 times y to the positive 1/2. So then if I square g prime of y, I'm going to square 3/2 y to the 1/2. So then g prime of y squared is going to be 9/4. Y to the 1/2 squared is just going to give me y. So now I'm going to plug this into my arc length formula for g prime of y. So then my arc length, again, they're giving me my bounds from 0 to 4 of the square root of 1 plus 9/4 y dy. So I am going to have to do a u sub before I integrate. So u is going to be equal to what's under my radical, so 1 plus 9/4 of y. My du will be 9/4 dy. So then I have to divide a 4/9 out of my integral. So I have 4/9 times. Now remember, because it's a u sub, I need to rewrite my bounds. So now remember, my bounds are in terms of y. I want to write them in terms of u. So again, in terms of y, my upper bound was 4, my lower bound was 0. So when I plug in a 4, so 1 plus 9/4 times 4 is going to give me a 10. When I plug in a 1, I'm going to get a, when I plug in 0, 1 plus 0 is 0. 1 plus 0 is 1. So then my lower bound will be a 1, my upper bound will be a 10. And I'll have, again, square root of u, which is u to the 1/2 du. So then to find my arc length, it's going to be 4/9 times, again, when I integrate u to the 1/2, that's going to be a u to the 3/2 times 2/3. And again, I have to evaluate this from 1 to 10. So I multiply 4/9 times 2/3. That's going to give me 8/27 times. It's going to be 10 to the 3/2 minus 1. And that is my final answer. You do not need to simplify that. Now, the one thing you need to make sure when we're talking about arc length, some key words to remember that are flags that you may need to use your arc length formula. If they ask you about perimeter around curves, then you're going to probably be using your arc length formula. How far did something travel? And the one thing, especially when you're dealing with FRQs, suppose they give you a graph or they give you a function, and they want to know the perimeter. One thing you have to consider, your arc length formula is only going to calculate this distance right here. So depending upon the problem and its way it's worded, you may have to take into consideration the distance from your axis back to the origin or back to the original starting place. The arc length is only going to give you this part right here. So there are examples, especially in a lot of FRQs, where you'll find your arc length, but then you may have to add this value wherever it hits the x-axis if they're asking you to calculate the entire perimeter. So that is your section 6.4.